Welcome to the colloquium of the Physics and Astronomy department. My name is Marcel Gleiser, and I just found out I was going to introduce David, which is perfect because I had something here in my hand just in case. So here it goes. So David is the senior scientist at the Planetary Institute, Science Institute in Washington, D.C. And he's also an adjunct professor of astrophysical and planetary sciences at the University of Colorado. So his research is, well, he's an astrobiologist, first of all. So he's interested in the development and origin of life on Earth and potentially in other planets around our galaxy and around the universe as a whole. And his research in particular focuses on climate evolution on Earth-like planets and potential conditions for life elsewhere in the universe. He is involved in many interplanetary spacecraft missions for NASA, the European Space Agency, and also the Japanese Space Agency. His research has been published in Nature, Science, and many other journals. And of course, he's a very sought-after speaker around universities and conferences and around the world. Right? Now, so that's one hat. And then he has many hats. He has one right there. But another one of his hats is that he's a very gifted popularizer of science. And he has done many TV shows and has written 3 popular science books, the last one being the latest one, not last, I hope, called Chasing New Horizons Inside the First Mission to Pluto, co-authored with Alan Stern, who's very much involved with Pluto mission, right? And he's written 2 other books. One is called Lonely Planets, and the other one is called Earth in Human Hands, which was written in part when he was visiting NASA scientists in the Library of Congress. So today he's going to tell us about Venus, what we know about Venus, what we don't know about Venus, and what we can learn from Venus, from our perspective on Earth. So
all right, thank you, Marcelo, and thank you all for coming out this afternoon and giving me an opportunity to talk about my second most favorite planet. Yeah, so I think that one is right? Hey, look at that. How do I go back to my presentation? Excellent.
You were a veteran.
Well, yes. So I want to talk a little bit about some missions to Venus and what we've learned and what we still want to learn with future missions. I'm going to skip some of the history pretty quickly because it's really, otherwise we'd be here all night. But one of the main reasons why Venus is so interesting is because, of course, of its climate, and it has played an interesting role in the history of our understanding of climate in general. Especially these days when climate is so much in the news and our discussions of it are so fraught. I always think it's so strange that when I learned about climate in grad school in the 1980s, before really, and when it was just really the beginnings of our current cultural freak out about climate, it was something I just learned about as a problem of planetary physics, an interesting physics problem of determining the surface temperature of a planet based on radiative transfer in atmospheres. But it's also true that the history of our discovery of climate change on Earth is intertwined with the history of our discovery of climate on Venus in a way that a lot of people don't know. And one of the points, the sort of intersection points, is this gentleman, Professor Arrhenius, who won the Nobel Prize a few years later in chemistry. But in 1896, he started looking at the role of carbon dioxide in climate, and he calculated that doubling Earth's CO2 would raise Earth's temperature by 5 degrees C, which, given the crudity of our knowledge at that time and the crudeness of his methods, is really not all that bad an estimate. But interestingly also, Arrhenius got interested in this partly through studying the planet of Venus, which was known at that time to have an atmosphere and some amount of carbon dioxide, although the composition of the atmosphere was still very much unconstrained there. But he also, using this same methodology, he did really the first climate model of Venus. And he concluded that Venus was somewhat warmer than Earth, but probably a pretty good place for life. And he said that everything there is dripping wet, and life near the equator should be luxuriant. So both of these are early examples of applying correct thinking to a problem, but with crude methodology and not really very good data. The notion that was implanted in the scientific mind by Arrhenius with these studies of Venus as a pretty Earth-like planet that was maybe somewhat more tropical than Earth, given its slightly greater proximity to the sun, but pretty much a similar planet. And that notion was reinforced by the fact that it was correctly deduced that Venus's great brightness is caused by globally encircling clouds that are highly reflective. Indeed, when you see Venus in the evening, or it just stopped being an evening star and it's going to reappear in the morning in a few weeks, but the reason why it catches our attention to the great degree it does and has for human cultures throughout history is because of that extreme reflectivity, which makes it the brightest thing in the sky other than the full moon. And so it was correctly deduced that they were clouds, but then it was incorrectly assumed that, well, we know what clouds are made out of. They're water. And so that makes Venus a swamp planet, a tropical planet. So there was some logic there, but again, with some incorrect assumptions. But this notion of Venus as a somewhat warmer Earth-like planet was really, since basically throughout the whole 20th century until the space age, that was the picture that was not just in a lot of fun science fiction books like, well, when I was a kid I read Isaac Asimov's The Lucky Star and the Oceans of Venus, in which our hero Lucky battles giant jellyfish and telepathic frogs under the oceans of Venus. It's a really good book, but Asimov put out another version of it in 1973 that I actually read when I was in 5th grade, where he apologized for getting the science wrong, and he republished it with an introduction that explained that this is no longer the way we think of Venus, kids, but it's still a fun story. Anyways, this notion was very persistent, and it persisted right up till the beginning of the space age. But then after World War II, we gained the ability to do radar astronomy, being what is Neil Tyson called it, being accessories to war. Our technology for observations in astronomy have often gained from warfare, like it or not, and radar was one of the fruits of World War II, and as soon as the war was over, people started pointing radio telescopes everywhere else off of Earth because they didn't need to just bounce radar off of enemy airplanes. And one of the first and brightest targets was Venus, and one of the first observations made was that Venus is putting out a huge amount of microwave radiation. And it didn't seem consistent with this idea of a dripping wet planet with luxuriant life. But there were alternate theories about that. Maybe it was because Venus was somehow really, really hot on the surface, and that was all thermal energy coming from the surface. But maybe other people said, no, it's probably just some upper atmospheric phenomena, some weird magnetospheric phenomena in the upper energy that's putting out energy in that wavelength, and the surface might still be okay. Well, the very first mission that humans succeeded in sending to another planet was this spacecraft called Mariner 2, which was launched in 1962 and made it to Venus in December of 1962. And it was basically justified in trying to answer that question. And it had one instrument on board, this microwave radiometer. It had a couple dust detectors and things, but the real instrument that was directed at Venus was a microwave radiometer. And it was designed to answer this question: was that anomalous microwave radiation coming from the surface? And it did this by looking to see if there was limb brightening or limb darkening. And I love this. I get to use a blackboard for a second. It's been years. I'll see if I still know how to use chalk. But the idea was you were going to take this radiometer and scan it across the disk of Venus and look for the shape of how that radiation changed spatially. So this is going across the disk of Venus. And the idea was that you would either get limb brightening, where it's brighter at the edges like this, or limb darkening, where it's brighter in the center. And if that radiation was coming from the surface of Venus, then you're looking through more air mass at the edges, and you're looking through less atmosphere right at the center of the disk, so you should have limb darkening. If the radiation is some kind of atmospheric phenomena, then you're seeing more of a signal at the edges and less in the center, and you should have limb brightening. And Mariner 2 made it to Venus. By the way, there was a Mariner 1. We don't talk about it so much because it ended up being what we call an oceanic mission. It landed in the Atlantic Ocean. But Mariner 2 made it and did this experiment, and there was a clear signal of limb darkening. And the answer came in: Venus is hot. And those jungle-like oceans of Arrhenius and decades of astronomers since him evaporated in that instant. And that notion of Venus as a friendly, life-friendly, Earth-like place vanished when this observation was made. And you know, it's interesting because this is the first experiment that was ever sent to another planet to answer a question. And it's also, I think, the best and almost the only example of a situation where you had a fundamental question about another planet. It was either going to be this model or this model, completely different, and you're going to do one experiment and it's going to tell you clearly this is right and that's wrong. I mean, that's not usually how it works. You get incremental knowledge, you learn a little bit, you rule things out, you argue over what it means. But I mean, when you get to do an experiment that's that clean and tells you the answer to a fundamental question, there are very few examples, and it happens to be the first time we ever sent another experiment anywhere. So that's kind of interesting. Anyway, so that was Mariner 2, and the results at first, it was quite a triumph, but it was also kind of devastating. This is this was from the New York Times the next week, an editorial, and it says Venus says no, and it says the message from Venus now reduces the hope of finding evidence in support of this the speculation of possible life elsewhere that has inspired philosophers and poets to one half as far as Auschwitz is concerned. Mars now remains our only hope of turning this universal dream into reality. The message from Venus may mark the beginning of the end of mankind's grand romantic dreams. What a bummer. We should never, ever have sent a spacecraft there. But I think the story gets a little better after that. After this, there were a succession of spacecraft that it took a while to understand just how thick and how hot that atmosphere were. The Soviet Union was particularly effective and successful at sending spacecraft to Venus. They had several entry probes that went down to find the surface and then stopped working at some pressure. And they didn't know, had they found the surface and had it just stopped working, or had it... And it turned out that they were not building these things to withstand 100 bars of pressure. And so it took a while. They had to keep building more and more robust spacecraft, but finally it was learned that the surface of Venus was 90 bars of pressure, and well, in terms of Fahrenheit, almost 900 degrees, or what is that, 460 something Celsius, or 730 Kelvin is how we always put it in our models. But anyways, and so, yeah, it was so extreme, it took several entry probes to just be built robust enough to finally find the surface. And I'm going to skip some of the history of figuring out just how extreme that environment was. In the 70s and 80s, there were several Soviet and several American spacecraft. There were Soviets notably sent a few landers that finally made it and survived for about an hour on the surface and took pictures. And the Americans had this great orbiter called Pioneer Venus in 1979 that really did the first in-depth study of the atmosphere and had a few entry probes. And so from that phase of exploration, we gained our understanding that Venus is not, I mean, it is Earth's twin in terms of its bulk properties, its mass, its size, its density. And what makes it such a fascinating place to me is that despite being Earth's twin in those regards, it's evolved in such a radically different environmental direction. And it's been referred to as Earth's evil twin, if you want. But, so we gained our sort of first order understanding of that, and then we began to have at least a cartoon understanding of how it got to be that way, how the two planets diverged. And then, since then, we've been doing a lot of work in trying to fill in the cartoon with actual quantitative theories. But this is what the cartoon looks like. You know, where did Venus go wrong? Well, it was born a little too close to the sun, and the wrong side of the tracks. If in this case the tracks are is the inner edge of the habitable zone, and so it doesn't have polar caps like Earth. It's hot and dry, and why is that? Well, if you have a planet like Earth and it has too much sun, you get a runaway greenhouse. And the cartoon goes, well, you just have a powerful positive feedback, and feedback here is represented, of course, by Jimi Hendrix. But if the surface temperature is higher, then you have more water vapor in the atmosphere. Water evaporates when it's hot. Water itself is a greenhouse gas, so that gives you greater infrared opacity, and that heats things up more, which causes more evaporation. And there's nothing to stop this. It's a runaway train. It's a positive feedback, and ultimately you end up with a steam atmosphere, and hydrogen escapes because when the water's in the upper atmosphere, it's very vulnerable to photodissociation from solar ultraviolet, and hydrogen escapes, some of the oxygen escapes, some of the oxygen reacts with mantle rocks, and then you lose your ocean. So, and the result is that today Venus has only about 1 in 10 to the 5th the amount of water that Earth has. So that works, but then we don't really know when that happened or how it happened in detail, and that's been sort of our state of knowledge of the evolution of Venus for a long time, really since 1979. But a major breakthrough in at least understanding the surface evolution, which of course is tied to the atmospheric evolution, came in the 1990s with the work of this spacecraft, which is called Magellan. Magellan was our first radar orbiter of Venus. And that solved the problem of how do you image the surface. One of the vexing things about Venus is with those bright, reflective, globally enshrouding clouds, you can't see the surface. It's not just from Earth you can't see the surface, as you can with Mars. With Mars, you can see the surface with a backyard telescope, and you can see markings that move around with the seasons. With Venus, even from orbit, you can't see the surface, but with a radar orbiter, you can, because this thing with that big dish antenna on top. Again, this is a spacecraft with one experiment, and that big dish antenna orbits Venus. Here it is being launched from the space shuttle, so those solar panels are not yet unfolded. And it still has its rocket motor that's going to fire it towards Venus and then separate. But what you do is you orbit, and this is side-looking radar, which it basically works like flash photography, where the radar can make it through the clouds. So you send a pulse towards Venus, and then you get that pulse back, and you do it over and over again, and you can start to build up images of the surface. Yeah?
What about the Russian missions?
So the Russians did the first, they actually did the first radar orbiter, but it wasn't global. They did some swaths, the Venera 15 and 16 missions, and that's important history. Thank you for mentioning it. They did the first radar imaging of a couple patches in the northern hemisphere, which verified the value of this technique. And then Magellan was the first dedicated orbiter that systematically mapped the entire surface. Yeah, so it wasn't the first time the experiment had been done. And in fact, we did see some really interesting stuff in those limited areas they were imaged by the Veneras, which made people want to see the rest of it. So briefly, this is what we found with Magellan. And this is, sorry about the false color, but which NASA somehow likes to make Venus red, because, and this came out weird, this slide, but because they think black and white is too, I don't know, unsexy or whatever. But of course, it's the grayscale images, this radar data. And the brighter stuff is rougher, and it's usually higher altitude. And the smoother stuff is smoother. I don't know why this slide came out really weird. I'll show you some better ones in a minute, but maybe it's just my vantage point. No, it really is weird. I mean, it looks kind of cool, but it's not supposed to look like that. But anyways, what we see is a planet that's dominated by smooth, very smooth plains, and it turns out they're vast plains of flood basalts, like you see in the, like in the Pacific Northwest, the Columbia River Basin, or places like that. And then there are smaller, very rugged highlands, and you can see there's this big equatorial band of highlands that's called Aphrodite Terra, and then some other provinces of highlands as well that are very rough. And about 15% of the planet are these rough highlands areas that are sort of analogous to continents on Earth, although not exactly. And the rest of the planet is mostly smooth plains. Now, those highland areas, oh, this looks much better. Those highland areas are mostly this stuff, which was named actually by the Russians, was named tessera, which means tiled. We're trying to give it a title that doesn't imply a theory of origin, but just describes its appearance. But this is very rough, very highly tectonized. You can see more than one direction of disruption. And these are the oldest features on Venus. And they may be analogous to, on Earth, the sort of continental cratons, you know, the areas, the really ancient granitic areas that underlie the old continental areas, like there's the Canadian craton and so forth. At any rate, these are really the most ancient features on Venus, these tessera, and most of the rest of the planet are these smooth plains. And you can see wherever the two intersect, the smooth plains embay or cover up the older, rougher area, which is, you know, by basic geologic principles of superposition and cross-cutting, tells you that the rougher stuff is older and this stuff, the smoother stuff, is younger. And this is a feature called Alpha Regio. And interestingly, all of the features on Venus are named after female deities and famous dead female people. That's a weird way to say it, but you're not allowed to name planetary features after living people. So they're named after famous women and famous goddesses. Except for 3 features do not follow that convention. Those features are named Alpha, Beta, and Maxwell. And those were the 3 features that were discovered from radio telescopes on Earth before this convention was adopted. And they decided to leave those names intact. So Alpha and Beta, that makes sense. They were the first 2. But strangely, Maxwell is the highest peak on Venus. And it's the only feature named after a dude. So I don't know how you want to interpret that. Put that in your Freudian pipe and smoke it. But that remained, and Maxwell, of course, after James Clerk Maxwell, the famous, you know, whose work made radio astronomy possible. So there's some logic there, but I don't know. Maybe there should be a contest, and we should go back and rename that peak to be consistent with the convention. Just a few more pictures of what Magellan revealed. Here's some more tessera, and you can see it's embayed again by the smooth volcanic plains. And then this is an impact crater. And one thing you don't see on Venus are very many impact craters compared to, think of other planetary surfaces. The moon, of course, Mercury, Mars, the icy moons. On almost all of them, you see a certain population of craters. You see almost none on Venus in a lot of the images. There's one. I'll get back to that point and what it seems to be telling us. The other thing we see on Venus is a vast quantity and variety of volcanic features. In addition to those smooth flood basaltic plains that dominate the planet, there is a huge number and variety of volcanic edifices. These are two giant shield volcanoes. They're sort of Hawaii, they're roughly the size and shape of the Hawaiian Islands here, and you can see they have rift zones running through them, and then these are lava flows running off the peaks, the high peaks of these shield volcanoes onto the smoother plains, and you can see that younger flows are rougher and the older flows are smoother because they're eroded and covered up with dust and so forth. It's quite beautiful, I think, these flows coming out onto the plains. And again, you can see a few impact craters, but hardly any. Just a couple more pictures of different kinds of volcanoes on Venus to show you the variety. These are nicknamed pancake domes or steep-sided domes. They're somewhat analogous to some undersea, to seamounts on Earth. And they seem to be made out of a very different kind of magma that's less viscous. And when you have very inviscid magma, it tends to pile up in these steeper domes and solidify in that kind of form. Just for scale, these are about 10 kilometers across and a few thousand feet high. So, you know, if you were in reasonable shape, you could easily hike one of these in a day, or, you know, Marcella could run it in an hour. But, you know, but it's the kind of the scale of what you would do on like a good day hike, you know, a healthy day hike, one of these. This is another feature, believe it or not, a volcanic feature. It looks like a river. In fact, it is a river. You can even see where it's meandered here. There's a meander, there's a delta. A lot of the same features we see in rivers on Earth, but on Venus, you've got to remember it's, you know, it's almost 900 degrees there, and so there are certain compositions of magma that stay liquid for long periods of time and behave as rivers. In fact, some of the longest channels, river-like channels in the solar system, are found on Venus, cutting through these plains, running for thousands of kilometers. So there's a real diversity of volcanic features. And this is actually one of those impact craters, although it's unusual with this outflow. And this is one of the kinds of craters we see on Venus, these outflow craters. And this is believed to be because you're impacting into a surface that's already so hot, you're closer to the melting point of these rocks. So the partitioning of energy in that impact goes more into melt than on a lot of other surfaces. So you tend to generate a lot of impact melt, and you get these really kind of artistic-looking outflows from a lot of these craters. Now, I want to talk just for a second about the crater population on Venus, because it's weird and revealing. This was actually one of the first press release images that came out of Magellan. Magellan mapped Venus from 1990 to 1994 and really revolutionized our ideas in a lot of ways. This was one of the first images released, and it's kind of iconic in a way. It's nicknamed the Crater Farm. And I remember seeing this image and looking at it with some colleagues. I was doing my postdoc then at NASA Ames with my advisor and mentor, Jim Pollock. And I remember looking at this image with him and going, like, wait a minute, something's not right here. And what is it that's not right? This is emblematic of the way a lot of Venus looks. And what's strange is that you have this surface that's very smooth and uncratered, and then you have this very small population of craters that seems superimposed on that surface. And if you look around, if you look at these craters, and basically all the craters on Venus, you'll notice that they're superimposed on these smooth plains, but the plains do not overlap the craters, and there's no sign of any older craters that predate the plains. So it's as if Venus was somehow completely flooded with magma in a way that wiped out all the older craters, and then a small number of craters were thrown at the last minute, like, you know, God said, oh, we better add some craters, and sort of haphazardly threw some on top as the last thing. It's very different. You know, if you look at, say, the lunar surface and you look at the lunar maria, which are also flood basalts, you see some of these palimpsests, some of these rims of older craters that are just barely covered up, poking through. You don't see that at all on Venus. You don't see any signs of craters that predate the flooding. So out of this came an idea that was very controversial, and is still somewhat controversial, and maybe was overstated, but I think is basically correct. And that is the idea of catastrophic resurfacing, that there was a time between 500 million and 1 billion years ago when Venus was completely covered over with magma to a depth that wiped out all the older impact craters. And then it stopped. And it stopped reasonably abruptly. And you know that because if it stopped slowly and kept going for a long time, you would see some craters that happened during the flood, and you'd see some that were partially covered up. And you almost see none. There are a few that people argue, oh, maybe that one's a little covered up, but generally it's remarkable. And the other piece of data is that if you look at the global distribution of the data set of the craters, they're really randomly distributed. And people have done this mathematically and shown, this is all the craters on Venus on what kind of projection is that? It's not a Mercator. Anyways, it doesn't matter. This is a map of Venus, and these you can see they're pretty random. And people have shown mathematically that it's really indistinguishable from a random geometrical distribution. So again, you don't see areas that are older and younger, and that's weird. For instance, contrast this to the surface of Mars, and these are all the craters on Mars, and you see a clear difference between the ancient southern highlands and the northern plains, which are much younger on Mars, and they are much more sparsely cratered. On Mars, you can tell the older areas from the younger areas by the crater density. And that's true of most planetary surfaces. It's certainly true of the Moon. The highlands are much more densely cratered than the Maria, because the Maria are younger. And there's another factor, which some of you may have already jumped ahead and thought of. Well, wait a minute. It's not a fair fight, because on Mars, you have all the small craters. Another factor of Venus is that there are no small craters, and that's because of the atmosphere. The dense atmosphere will filter out anything smaller than about 4 kilometers. It will not hit at a hypervelocity. It'll waft down and go thud, and it doesn't make a crater. So there is a filter, and that's, Mars, it's dominated by the small craters. But nonetheless, if you remove the small craters from Mars, you would still see a clear difference in age between the south and the north. And you just don't see that on Venus. So that's another piece of evidence, that uniform age, that something happened globally around probably about 700 million years ago, but there's a big error bar. We don't have any direct samples and age dates from Venus. We just have the statistics born of crater counting and the data we have about fluxes of objects in the solar system and the models you do to connect that with sizes of craters. It's a little bit indirect, but so that's why there's an error bar. But 700 million years plus or minus 200 million years, there's that pretty uniform age. And the question is, what happened? But even in the absence of knowing what happened, just that fact puts Venus in an interesting category with the Earth, and very different from other planets. Because this is a histogram of how old surface rocks are on these different planets. And this is just a cartoon drawn by my colleague Jim Head, but you get the idea. On Earth, if you try to find a 3 billion year old rock anywhere on the surface of the planet, good luck. If you try to find a 2 billion year old, there are a few places you can find a 1 billion year old rock on Earth, but it's very rare. Mars, by contrast, try finding a rock as young as 1 billion years. You won't. 3 billion years, 4 billion years, and the Moon and Mercury, there's a class of planet where you're doing mostly forensic geology, trying to understand processes that stopped a long time ago. For all we know, Venus could have been one of those, but with Magellan, we know that Venus is in the class that Earth is in of being recently active in the last billion years. Now, there are question marks there. Is it still currently active? I'll come back to that. But certainly, in the overall types of planetary history we know about, in the sort of scale of ages of activity, Venus is a survivor in the way that Earth is. And that makes sense in terms of sort of crude principles of thermal physics. The reason why Earth is still active and Mars isn't is because surface to volume ratio, bigger objects hold their heat. Earth is hot and churning and active, and Venus is the same size as Earth, so maybe you would expect that. But of course, there's some important differences. So out of this came this idea, this observation that this massive this global surface of flood basalts that we see that covers much of the planet was the result of a resurfacing, an event may be too extreme a word, but a resurfacing epoch that occurred in the last billion years and then stopped. And you can see signs of this flooding on the surface in a lot of places. And I got really interested, along with some colleagues, in the question of what that would have done to the atmosphere of Venus. Because another thing that volcanic resurfacing does is outgassing. And you can model the composition of gases that should be outgassed with magma on Venus. And you can model the volume of different gases you should get with different abundances of, with different volumes of, the volume of magma that would be required to have sufficient depth to cover up those old craters. And you can say something about what the inputs into the atmosphere were like. And out of that comes the question of, I mean, that's a pretty radical change on the surface. It's a lot of greenhouse gases and other gases you would have been pumping into the atmosphere. What would that have done to the climate and the clouds? In order to answer that, some friends and I, some colleagues and I, created some models that were specifically created, at least at first, to address these questions. We wanted to know 700 million years ago, what were the atmosphere and climate like? Because given those outgassing rates that you can put some bounds on. And so we created what we call the Venus climate model that basically time steps the atmospheric composition based on a source of volcanic outgassing. We include different kinds of escape from the upper atmosphere. Importantly, we included surface atmosphere chemical reactions because it turns out that they end up being key in this. And the sort of core of this was a radiative transfer model, which if you're interested, I can tell you the details of, but I won't now. But it's a one-dimensional correlated K model for those of you that means anything. Anyways, so the point is we were able to rapidly calculate the climate for changing atmospheric composition in a time-stepping way, and we put in a cloud model that responded to changes in the atmospheric composition and chemistry. And we put all this together, and then we could induce events like a volcanic outgassing event and see what happened to the planet with the change of radiative properties of the clouds and the change of infrared opacity and scattering in the atmosphere. And infrared scattering is very important on Venus, by the way, those of you that think about atmospheric physics. On Earth, you can get away with just usually not worrying about scattering by infrared, but in an atmosphere that thick, you have to worry about that, and that's in there. And then you let the surface and the atmosphere interact chemically, and you can imagine there are going to be some weird feedbacks in this system, because if the temperature changes a lot, which it does with the changes in atmospheric composition, then that changes the equilibrium point of the surface reactions that also buffer some of these same greenhouse gases. Most importantly, sulfur dioxide is buffered by reactions with surface minerals, and sulfur dioxide is the second most important greenhouse gas on Venus, other than carbon dioxide, and then comes water, even in its minute amount. So these greenhouse gases are changed not just by volcanism, but by surface atmosphere reactions, and then you have to worry about diffusion into the surface, and it gets all really complex. But the behavior is interesting, and without showing you a lot of results, because I want to move on to a few other things, what we found is that this change in outgassing rate can lead to huge changes in climate of order of 100 Kelvin. And those of us here on Earth were worried about 2 and 3 Kelvin is worrisome, and then throughout history we see episodes on Earth of 10, but 100 is crazy. But that's what we derive from this. And not only that, but it turns out that sources of outgassed SO2 in the recent past, meaning the last 10 million years or so, seem to be necessary to maintain the clouds. In other words, if you turn off all the volcanoes on Venus, after 10 million years the clouds are going to go away because the atmosphere sucks up the SO2 with reactions with minerals. And if that is right, that means that answers the question about currently active volcanism, currently active geology on Venus, because it means that when you go out at night and you see Venus with your naked eyes and it's that bright and reflective, you're seeing the results of volcanism on the surface in the last 10 million years supporting those clouds. This is all model dependent, of course, so we still want to find what people call the smoking gun, seeing an active volcano on the surface of Venus. We haven't done that yet, but we've gotten a little closer to it, as I'll show you. And I don't think I have a slide about this, but subsequent, because I move on to other things, but subsequent to this, we found some evidence, geological evidence of these climate changes, places where there is faulting of the surface and polygonal structures and other geological structures that are hard to explain but become explicable if you include this extreme temperature change on the surface and the stresses, the thermal stresses from that propagating into the interior. So we think we found geological evidence that supports this notion of radical climate change on Venus in the, well, I don't know if I want to say the recent past. It depends on if you're a cosmologist, then 1 billion years ago is the recent past, right? If you're a biologist, well, maybe it is. If you're a historian, it's not. Anyways, for planetary science, that's the recent past. What happened to this slide? I guess that's weird. Oh, anyways, so out of this, we started doing, and we've been doing really now for many years, what we call Venus system science, and analogously to Earth system science, where we look at the interactions between the different domains of the planet, between the atmosphere and the surface, with chemistry and outgassing between the surface and the interior, with thermal fluxes and volcanism, and how climate manifests as a function of all of that, and then propagates thermal stresses and affects reaction rates on the surface. And of course, clouds are important to a part of that. And then there are external forcings with the solar cycle and the occasional comet impact, which it turns out comet impacts can be pretty important for the atmospheric evolution of Venus, because Venus is so dry. If you add up all the water vapor in the atmosphere of Venus, it's something like 5 × 10⁻18 grams. And one large comet has that much water. So if you threw, Comet Halley into Venus, you would double the water abundance in the planet with one impact. And remember, water is the third most important greenhouse gas on the planet. So comets have an interesting role historically in the climate there. Anyways, what about the early history of Venus? What about this vexing question of water? Now there's almost none in the atmosphere. There's about a 3 centimeter equivalent if you condensed it all on the surface. Interestingly, that's the same amount of water as Earth and Venus have the same amount of water in their atmosphere. But of course, on Earth, we have this massive reservoir on the surface that Venus doesn't have, so there's 100,000 times as much. How did it get that way? Did Venus ever have oceans? I'm going to do this part quickly, but there's circumstantial evidence that it did, but no direct evidence. There's the deuterium to hydrogen ratio, which is much higher on Venus, which suggests a lot of escape of hydrogen, which probably means loss of water. Doesn't prove there was surface water, but it implies it. There are formation models, almost all of which show Venus and Earth forming with similar water abundance because they formed out of the same reservoir material that was a lot of gravitational scattering, and it's just a sort of an Occam's razor argument. You don't segregate all the water into this planet and none of it on this planet if you're forming out of this messy scrum of orbiting and scattering bodies. Our best climate models with a faint young sun suggest that you probably had abundant liquid water on Venus when it was young. So none of this is a proof. We would still like to go back with spacecraft and find those rock samples that tell us that Venus was a wet planet, or more direct evidence. But our best ideas and the evidence we do have points in this direction. But then how long was the ocean there? And there are huge uncertainties in this. And this is an old slide because it's no longer true, but for a long time clouds were excluded from the best published models, and for that reason nobody really knew. There were these models that everybody quoted by Jim Casting at Penn State that said the oceans went away in 600 million years, or less, but nobody knew. And then about a decade ago, Mark Bullock, who was my former student, and I did some very crude models where we included cloud feedback, which hadn't been done before. But it was just a really simple one-dimensional model. And it told us that the clouds really stabilize the ocean. And we got a timescale of possibly 2 billion years for the persistence of an ocean on Venus, which is a really different picture. But we weren't sure we believed it. And we published this and said, well, this is a really crude model, but people need to do this in a full-up GCM, which is hard to do. But it's finally been done. And this was published, I guess, in 2016. I should know since I'm a co-author. But with this provocative title, was Venus the first habitable world of our solar system? Because we finally took a full-up Earth GCM, the same kind of model we used to predict climate change on Earth, and adapted it well to Venus. And without going into too much detail, we find that there are a lot of behaviors that the atmosphere takes on which do sort of protect the ocean, and the oceans persist for a long time. And we had to make some assumptions about topography and things that aren't well known. But it's pretty interesting what happens in this model. The clouds act in such a way as to keep Venus cool for much longer. Because what they do, and this, it depends on the rotation rate, and so we had to assume the history there and a lot of things. But what they do is, on a slowly rotating planet, if you put in a full circulation model, the clouds organize themselves so that the sunward-facing hemisphere is permanently cloudy. And so that the anti-sunward, or the nighttime hemisphere, is cloud-free. And it stays that way. And if that's really happening, if you think about it, if you were a civilization trying to geoengineer your planet to keep it cool, that's what you would want to design, because the clouds act as a sun reflector on the sunward-facing side, and yet the night side can cool efficiently to space, just as in a clear night it gets much colder here on Earth than on a cloudy night, because without clouds the ground can radiate right to space. And that happens, and it keeps Venus cool for billions of years. And so we do get that it seems that when you do this with the GCM, the oceans can persist for billions of years. And that's pretty wild, because if that's true, it means that on our solar system there were these two neighboring habitable planets for about half the age of the solar system. It's not the picture we usually have, that Venus was a watery place early on and then it went poof. And it's been the way it is now for its whole history. So I think there's a lot more work to be done, and there are a lot of assumptions we had to make here. But it's pointing towards a really interesting possibility that there could have been these two habitable planets. And then that leads to all kinds of fascinating questions about origin of life, because these planets have been exchanging material over time, with flinging rocks at each other occasionally, and bacteria can survive on rocks, and so you may all be Venusians. That's what I came here to tell you. If there's one thing you take away from it. So anyway, this is an emerging picture, and there's a lot of work to be done. And it also has some really interesting implications for exoplanets, for Venus-like exoplanets, and for just the question of the inner edge of the habitable zone. Planets closer to their stars, do they start off habitable, and do those almost what I would call metastable habitable conditions persist for billions of years before they lose their oceans? Even a planet that's outside the habitable zone in terms of equilibrium modeling may be metastably habitable, if that makes sense. So anyways, we get this model. I don't want to belabor this, but the idea that maybe the oceans weren't lost till about 2 billion years ago. And maybe that helps explain why Venus is so strange geologically and so different from Earth, and seems to not have plate tectonics, which I haven't really mentioned, but plate tectonics are the organizing principle of geology on Earth. And so one of the big questions with Magellan was, are we going to find plate boundaries and chains of volcanoes and mid-ocean rifts and all the things we associate with the churning of and colliding and subducting of plates on Earth? And we basically don't see it. And it may have to do with the fact that Venus dried out in this way, because now we know that water lubricates plate tectonics on Earth. And if you dry out on Earth, plate tectonics will probably cease. And when they cease, you will probably get a global resurfacing event, because all of a sudden the mantle heats up and it becomes unstable. And this has been modeled. And so there is a possible connection here with the drying of Venus, the mantle becoming desiccated, global subduction, and massive outpouring of plains, and then disturbance of those plains, and then localized volcanism that we see today. So there's a lot still we want to investigate with future missions, but the picture we're getting here is maybe consistent with this global drying of Venus, leading to the seizing up of plate tectonics and leading to this change that we see in the tectonic and volcanic style. Just quickly, 2 more missions. There's a story that I could tell you if I had more time is the massive struggle since Magellan to get a new American Venus mission. And I've been in the trenches with this, and it's been like Charlie Brown in the football, where we keep thinking we're going to get another Venus mission, and they offer us, we write proposals and go up to kick the football, and it gets pulled away, and we go whomp and fall on the ground. And it's been kind of frustrating for years. But we've been saved a little bit by our international colleagues. Both the European Space Agency and the Japanese Space Agency have sent more recent Venus missions that we've been able to participate in. Less ambitious and sort of smaller. Orbiters, was their first Venus mission, and now the Japanese have their first Venus mission. So they're, in a way, they're baby steps, but they're also very sophisticated little spacecraft that are doing a lot of cool things. And I don't have time to go into this full payload, but the Venus Express was launched in 2005, got to Venus in 2006, had infrared and thermal spectrometer, ultraviolet spectrometer, an amazing Fourier spectrometer that unfortunately was the only instrument that never worked for a really dumb reason. It's so painful when you send a spacecraft to another planet and you know there's something, if you could just take a hammer and go, it'd be fine. But this thing, the hatch never opened. Instruments working fine, we know that, but it's taking spectra of the hatch. And they tried spinning the spacecraft and shaking it and turning it thermally towards the sun and away from the sun. Never opened. Anyways, but cameras, everything else worked great. I'm not going to go into this whole payload now, but Venus Express, what it did was, it was really our first weather satellite at Venus. Long-term observations of the changing dynamics of the atmosphere. And that's been really cool. This, for instance, these are cloud motions that you can't see if you just look at Venus with a visible, because these are in the mid-atmosphere. But if you look in the mid-infrared, then you're seeing below the surface, and we discovered this whole other realm of cloud dynamics that reflect the circulation happening at deeper levels than we had seen before, and allowed us to put together a 3D, or really a 4D picture of the atmosphere and how its dynamics are changing over time. We also discovered these bizarre polar vortices at both poles. There are these permanent sort of upside-down tornadoes, these vortices at the poles, and they turn, sometimes they become binary or even ternary, where there are 2 or 3 of these whipping around each other, and then they become singular again. So these really bizarre dynamics at the poles we didn't know about before that. I'm going to skip through a couple things here because I want to try to stick to time, but we discovered radical changes over time in the amount of sulfur dioxide above the clouds. This had been observed before, and we weren't sure it was real from earlier spacecraft, and then Venus Express found really elevated SO2, so it seems to come and go. That is interpreted by some as evidence of massive volcanic eruptions on the surface that pump SO2 into the stratosphere as they do on Earth, although that's not, as with many things on Venus, it's still not a universally accepted explanation. There's some other possibilities. I'm going to skip that. But about active volcanism on the surface, Venus Express found some really interesting indirect evidence for what they called recent hotspot volcanism. And this was because even though it was an atmospheric mission primarily and an orbiter, we learned in the 1980s and 1990s, you can see the surface of Venus from orbit and even from Earth in a couple really narrow spectral windows. There's this 1 micron window where it's very narrow, but where the absorption by SO2 and CO2 and water is the optical depth is less than 1, you actually get photons from the surface at in this narrow window. And at that wavelength, they were able to map the emissivity of the surface. And it's really tricky because you have to separate out the thing that dominates is the topography, because it's colder on the mountaintops, the emissivity. It's colder on the mountaintops and hotter in the lower altitudes. So you take the radiation at 1 micron and you compare it to a topographic map from Magellan, and you model what the difference in radiation should be with the topography, and then the residuals are telling you something about the composition of the surface material and the changing emissivity. So it's a little dicey, but when you do that, you see that some of the places that look like recent volcanoes have different surface composition. And they're different in the way that the chemistry tells you is consistent with young lava flows. So this is indirect, but it's more circumstantial evidence of recent active volcanism on Venus. Now we have in orbit the first ever Japanese mission to Venus, which is called Akatsuki. And here are some cute Japanese characters for Venus and Akatsuki, and they're very much in love, it turns out. This spacecraft has a weird story, which I'm going to tell you really quickly, which is it launched in 2010 and made it to Venus. It's a little spacecraft. It's like the size of a washing machine with little solar panels and a small payload of some really cool instruments. And, oh, by the way, here I am with Akatsuki at Sajimahara, which is the Japanese sort of equivalent to JPL, and there's the spacecraft before it was launched. And when I went there with some colleagues, it was pretty wild because you put on your bunny suit, and you walk into the clean room, and we're walking over, and I'm like here, and here's all these electronics. These are the instruments. These are panels that are sort of folded up on the inside of the spacecraft here, and then it gets launched. And we're standing there looking at it, and one of my colleagues goes, "Oh, that's really neat. Where's the actual flight model?" And they go, "Oh, this is the actual flight model." And I was standing right there, and if I had tripped, I would have just gone and could have knocked. If you go to like JPL or Lockheed Martin clean room, you know, there's like flashing red lights and fences, and you can't get any closer than that. You know, it was very, all sort of casual. But anyways, it worked like a charm. It got to Venus, no problem. And then something horrible happened. There was a 12-minute rocket burn to go into orbit around Venus. This was in 2010. And it was going to happen while the spacecraft was behind Venus, so no direct monitoring from Earth. And then it was going to come out from behind Venus and send a signal and say, "I'm here, I'm in orbit, I made it." And after that 12-minute rocket burn, during that 12 minutes, something went wrong. And the rocket stopped firing, and it did not go into orbit around Venus. Turned out later, we found out that there was a clog in the fuel system, and part of the rocket blew up. Anyways, it went spinning helplessly around the sun. And it was really, really sad knowing these people who had worked on this great mission, and it was their first ever interplanetary mission, or first ever mission to Venus. They'd had an asteroid mission. And we all had high hopes riding on it. And the thing went spinning off around the sun, but it turned out it was spinning helplessly around the sun on a trajectory that was going to bring it back to Venus in 5 years. After passing close by the sun a few times, which it was not designed to do, and so nobody knew if it would survive those close passes to the sun. It didn't have the thermal protection. And then they didn't know if they would be able to get it into orbit around Venus, because it turned out the main engine was gone. They didn't know that at first, but it was. But also, in addition to the main engine, there were these little maneuvering thrusters, 8 of them. And they're not designed to fire for more than a second or two at a time, these little bursts to maneuver once you're in orbit. But they figured out that if they fired them all at once in the same direction for 20 minutes, they would have enough thrust possibly to get into orbit. And they couldn't practice this because they only had enough fuel to try it once. So 5 years went by. Most of the team dissipated and went off to doing other things, and that's one of the tricky things about this. You don't sit there for 5 years. You have to find another job. Anyways, long story short, or long story long, it worked. They're now in orbit around Venus. Skip some of this, but not on the planned orbit. The planned orbit was going to be circular and was designed to match up with those weird cloud movements in the middle atmosphere and follow along with the cloud movements and study the clouds. So they had to reinvent the mission. Instead of a 30-hour orbit, it's on a 10-day orbit. And instead of a circular orbit, it's in this really extremely elliptical orbit. But that allows you to do certain things. At part of the orbit, you're really far from Venus, and you can take whole Venus images. And part of the orbit, you're really close, and you can take very detailed spectra of certain areas. So it's an entirely different mission, but it's there now, and it's actually made some really cool discoveries. This is a photo of, with the IR camera, that 1 micron region I mentioned, showing you that you are seeing emission from the surface. These are differences. This is a mountaintop where it's colder, and these are plains where it's warmer. So you're seeing differences at 1 micron. And so we're hopeful that collecting a lot of this data and analyzing it will allow us to possibly discover active volcanism on Venus. But you can also see the clarity of the images. This is that same middle atmosphere kind of opacity that I showed you images of from Venus Express. Look at the incredible detail. So we're getting tons of amazing images of regions of the atmosphere that haven't been well imaged before, and that's telling us about the dynamics and how things are moving around and really how that climate is functioning. And there's another really strange thing that Akatsuki has discovered, and that is this feature, which is in the middle cloud, so it's 50 kilometers up from the surface. But what's really weird, is that it stays in one place relative to the surface. So Venus rotates very slowly. Once every 243 Earth days, it's rotating really, really slowly, and it's backwards from Earth, so that if you were on Venus, the sun would rise in the west and set in the east. But the atmosphere whips around in what we call the super rotation, much faster than that, in 4 days only. And so the idea that a feature in the clouds would be connected to a feature on the surface seems to make no sense. And yet, there it is. And Akatsuki found this, and they keep observing it, and it stays. This is above the highest mountain range on the surface of Venus, 50 kilometers up. For some reason, there's a persistent cloud feature. I mean, think of that, 50 kilometers. That's much higher than clouds on Earth. And so we think it has to do with what we call gravity waves. Not to be confused with gravitational waves for you cosmologists in the audience. That would be pretty cool if it was gravitational waves. But no, these are gravity waves, which means, and these are things we see on Earth, which are just atmospheric waves where gravity is the restoring force. And somehow there's some wave, we think it's propagating off the surface, propagating up 50 kilometers and maintaining this structure. But it's really strange. There's still a lot of mysteries. Let's see. I need to wrap this up because I'm over time. I got a little carried away. But all I'll say about future missions is that we're trying. We've had studies. This was a really ambitious one that that NASA commissioned, where we had a big new orbiter, a big new balloon, a big new lander, and then unfortunately the price tag for this came out at about $3 billion, and after NASA paid us to do the study, they said, ha, you're joking. So that didn't work. And then we did a smaller study. I was actually the science lead of this one, for one that would just be a climate mission that would have a balloon and some drop probes. The balloon, I'll just show you this because it's kind of cool. The balloon spends about 21 days and spirals upwards towards the pole, just riding the winds. So you cover a huge range in latitude and longitude and solar angle in those 21 days, and would have done a lot of really neat observations. I shouldn't say would have, will. But this study made it into, NASA does these decadal surveys you may know about, which are every 10 years they rank mission priorities for the next decade. Our study made it in as the 3rd ranked mission for this decade. The 1st ranked mission was a Europa mission. The 2nd ranked mission was a Mars sample return. Both of those are being funded. Ours didn't make the cut. So we were number 3, we didn't quite make it. And yet we persist. I have a few more slides of possible future missions, which I won't show you because I'm out of time, but basically what they really amount to, a lot of the missions that are being proposed now are taking pieces from this flagship mission and proposing them as smaller missions. So just a lander, or just a balloon, or just an orbiter. And there are several missions that are proposed. And if you do it that way, you get the price tag down to, in the hundreds of millions of dollars range, which is an easier thing to run by to get through the NASA machinery than at the multi-billion dollars, which NASA does about one mission per decade of that scale. They're called flagship missions, but you have to, it's very hard to get one of those. So we're still trying. Meanwhile, our international colleagues are carrying the ball for us, and I'm hopeful that we will keep kicking the football, and one of these days Lucy won't pull it away. We'll have new Venus missions. Oh, two final slides. So one of the things that's helping us is that there's this realization in the community that Venus is really important for understanding a lot of the exoplanets we're finding. That there are a lot of exoplanets that are possibly Earth-like, but possibly too close to their star, but we don't really know where that inner edge of the habitable zone is or how it evolves over time. So all of a sudden, we find that there's a lot of new support for Venus missions coming from the exoplanet community. And those of us who've been pushing for these missions are very gratified that now some exoplanet people are writing white papers and saying, hey, you planetary people, you need to figure out Venus so we can do exoplanets. So that may be what saves us. But one final slide. This is a fantasy from way in the future where we have a Venus research station called Aphrodite Station floating in the clouds. And there's your granddaughter there poking her head out of this bathysphere and doing some science there on Venus. So maybe someday that'll happen. So thank you very much.
Yeah, so we're a little over, but maybe one brief question or two, and then we can retire to the tea. And plenty of further opportunities for questions. Yes?
In the beginning, you showed the whole surface picture of Venus, and you noted that the tesserae, I think you called them, were concentrated in that equatorial region. I'm kind of wondering why that might be. If there's no plate tectonics, like, why do you see such features there?
Yeah, it's sort of a little bit, that particular projection I showed you, I think exaggerates that a little bit. But it is true. There are two really large elevated features on Venus and a lot of smaller ones. And the two large ones, which are sort of analogous to continents on Earth, but people don't use that term because that means a specific thing about composition and dynamics, plate dynamics that may not apply to Venus. But one of those is roughly at the equator and sort of along the equator, as you noted. But the other one is near the pole. It's where that mountain Maxwell Montes is. It's called Ishtar Terra. So Aphrodite Terra is the equatorial one, and Ishtar Terra is the one that's near the pole. And you know, I have not heard any sort of proposal of that relates that in any mechanistic way. When you look at the actual map, it looks a little more random than that. It doesn't look as, I mean, it is interesting to ponder. I mean, there are some places in the solar system where there are equatorial features that are related to rotational dynamics and, you know, wander of, moments of inertia and things like that. I've not heard that proposed for Venus. And remember, it's a very slow rotator. So that would seem to argue against that being a factor. But it is an interesting observation.
I'll get several more